This video wants to present and demonstrate a package that I wrote in C# for representing and studying the log files produced by a medical robot. This device is composed by up to 25 motors in one of its versions that drive 2 robotic arms and a number of other subsystems. This package loads as an input data all the log files that have been produced during a real session. In this case, we are talking about more or less 2 hours and something, from 8:00 AM up to 10:30 of the 25th November. And this can be seen in this top scale. These log files are more or less 150, and each of them is represented by one of these rectangles. Being each log file composed by 5 megabytes, you can easily imagine that we are talking about half a gigabyte worth of data. This package is aimed, as I said before, to represent intuitively the contemporaneous activities carried on by the different subsystems. And this is done using this metaphor, which is similar to the Gantt diagram, and represents each concurrent activity on a horizontal stripe. So each of these stripes represents one specific activity. A rectangle, one of these stripes, for instance, represents a move. So during this period represented by the rectangle starting here exactly at 8:45, 26 seconds, up to 8:50, in this case represents a spinning of a centrifuge. If you click on the right mouse button on it, you will see a profile. So this dialog shows a number of kinematic properties of this profile and the mathematical graphical representation of the velocity on the vertical axis versus time. Of course, we can have much more complicated profiles. As you can see, the user experience is quite easy. We can easily zoom in and zoom out or pan the window on screen, and for instance show even much tinier moves with respect to the one before. This, for instance, is a much smoother move composed by 2 sinusoidal profiles and a rest period for synchronizing probably with other subsystem of the same arm. Of course, besides these kinematic moves, there are additional information. For instance, this is the so-called door locks. This instrument has a number of doors which can be opened, and there are specific sensors that show if the door has been opened or not. There are other kinds of stripes representing other different contemporaneous activities being carried on by the instrument itself. It is possible to show even data measured by the instrument. For instance, we can show the temperature measured in different places, adding to the aforementioned stripe different stripes. For instance, these 2 lines, this in green and this in violet, represent the temperature in 2 different positions of the instrument itself. There are even digital data. In this case, this is the action of a pump. There are analog data as produced. For instance, we can show in the same timeline the drive of the motors. In this case, this is something which is not available in this stripe of data. There are other possible digital information that can be shown and analyzed by the operator. The audience of such tool is rather big because it goes from VMV professionals, as I was, to field technicians to development engineers, as you can imagine. Basically, all this kinematic information, all this time-dependent, time-evolving information can be seen both in this metaphor, in this timeline metaphor, which can be very useful, but in a way it's limited to professional persons, but also in another, let's call it metaphor, which is that of the real animation. So we can define a period of time during which we are interested in the real animation of the action of the instrument itself, and then click on this tool. Well, the computer I'm working on now is my small portable PC, so my small notebook, so the performance is quite low and it takes a little bit time to load this animation. I would like to draw your attention on the fact that basically this animation has been pre-compiled, so all the data which are required to move each of these subsystems has been pre-compiled during the initial phase you've seen. As you can see here, we have a symbolic representation of the instrument itself. I will not enter into detail, but you can imagine different actors. For instance, this is a centrifuge, this is another one, and these are other subsystems devoted to incubating, moving fluids, reagents, samples, and so on. This, in the bottom part of the screen, is a symbolic representation of subsystems which cannot be represented in a map, in a plan, as it is in the top part. It is possible to tailor all this information contained in a changeable way in order to improve the user experience. For instance, it's possible to increase the plan of the instrument itself. What you see here, all this, let's call it nest, is actually the trajectory that the different subsystems, in this case we have two moving arms, walk through during the selected period. This is what we get when we start with a simulation itself. This is not exactly a simulation, it is more precisely a real playback of what has been stored during the real testing issue. As you can see, the move is quite jagged, it's not very smooth. The reason for this is the low characteristics, the low quality of the processor using by this notebook. In a quad core, which we normally use, the move is absolutely smooth, and you will see probably an MPG output of this. We can move faster. For instance, we can go up to speed number 8 times the normal speed, and you can see the different subsystems moving contemporaneously. Of course, now we have the centrifuge spinning, we have this internal ring filled up with reagents that's moving to keep the reagents suspended. It is a mixture of different parts, so it must be agitated to be suspended. So we can see this big round thing, which is the incubator, while a pipetter, which is this red point moving, goes to each of these vials. Each of these rectangles is actually a consumable composed by different vials containing reagents. Now we move in a little bit further situation. Here we can see a different move, which is okay. This is another arm which moves a gripper. This gripper is capable of moving all these consumables around in the instrument. For instance, now we see that this grip has taken one of these consumables and has put it into the centrifuge. Now, after a while, the centrifuge will start spinning. Now, what you've seen here is that the gripper went into this slit that goes to the, let's say, ground floor of the instrument, on which we have actually a drawer containing a significant number of consumables. Here is a symbolic representation of this drawer. This is the drawer, in this case featuring 7 columns, each of which is actually a structure containing these consumables. This is, for instance, the gripper, so the vertical move of the gripper. Now you can see that the gripper went down to place the card, the consumable, into the centrifuge. This other one is on the other side, the pipa, so the pipetter that is composed by a needle, a probe that gets into one of these positions to get water or to get reagent or whatever. And this one is a diluter, so a precision syringe that moves a plunger to get and dispense precisely defined volumes of liquids. This other part is a front representation, of course a symbolic front representation of the instrument, having all the doors that can be opened and closed to let the user make all the manipulation he needs. And this is a light emitter that closely resembles what is the situation. So if there is at the client side, at the customer side, a problem that turns out into an alarm changing the color of this light, you can simulate exactly when this happened and consequently try to find inside the log files what's the situation. It is even possible to store all this movie into an MPG file, which I will do then, that frees the customer from the need of using this package and can enable them to send MPG files that do not need a specific player to be played, can be played in a normal way or even published on a common site. So there are many other options which of course relate to the specific characteristics of this instrument. As a final observation, I would like to draw your attention on what is called RAV, Redundant Analytical Validation. This is still a prototype, but it's still already working, at least in the as a first prototype, that analyzes all the data which are only geometrical data and kinematic data that have been extracted from these log files in order to reconstruct the assays done. The aim of this tool is that to make a validation of the analysis, so verify that a number of specific moments called anchors, for instance the dispensation of a volume of reagent or sample into a column, which is one of these little vials that contain reagents, or the fact that one of these consumables has been put into the centrifuge, match to the prescribed assay specifications that are included in a specific file.